Did you know that somewhere out there in the vast darkness of space, there's a planet where it rains molten glass sideways? The universe isn't just strange, it's stranger than anything we could dream up. Every time we think we've figured it out, it throws another curveball our way, like a cosmic magician with an endless bag of tricks. And here's the wildest part. No matter how much we discover, it feels like we've only scratched the surface of something infinitely bigger, older, and more mysterious than we can even comprehend. That's the thing about the cosmos, it doesn't play by the rules we're used to. Black holes warp time itself, stars explode in symphonies of light and energy, and entire galaxies spin through the void like dancers in an endless ballet. But beyond the breathtaking beauty lies a universe packed with secrets, hidden facts so mind-bending, they'll make you question everything you thought you knew. What if I told you there's a place where time moves slower than on Earth, or that the night sky we see is actually a time machine showing us glimpses of the past? These aren't science fiction, they're real, and they're just the beginning. So buckle up, because we're about to take a journey through 30 of the most astonishing, spine-tingling truths hidden in the fabric of space and time. Some will make you gasp, others might leave you staring at the ceiling at 3 in the morning, wondering how any of this is possible. But one thing's for sure, by the end of this, you'll never look up at the stars the same way again. Ready to have your mind blown? Let's dive in. If you've ever blown up a balloon with dots drawn on it, you've already witnessed one of the universe's greatest illusions. The Big Bang wasn't an explosion in space, it was the explosion of space itself. Here's what that means. Picture every single point in the cosmos stretching outward at once, like those dots on the balloon spreading apart as it inflates. No dot is the true center, they're all just moving away from each other. This is why astronomers say the universe has no center. No matter where you stand in the cosmos, it would seem like everything is racing away from you because space itself is expanding in all directions. Those distant galaxies aren't actually speeding through emptiness, the emptiness between them is growing, and that shatters our everyday intuition. On Earth, if you hear a firework explode, you can point to where it happened. But the Big Bang happened everywhere simultaneously, even right where you're sitting now. 13.8 billion years ago, this very spot was part of that unimaginably hot, dense beginning. Think of it like baking raisin bread. As the dough rises, every raisin moves farther apart from the others, but no raisin is the center of the expansion. Now imagine that bread is infinite with no edges, and you start to grasp the true scale of our universe. It's not expanding into anything, it's all there is, stretching itself larger with time. This also means the night sky holds a cosmic sleight of hand. When we look at distant galaxies flying away from us, we're not special observers in those galaxies would see the exact same thing, with everything appearing to retreat from them. The universe isn't pushing us apart from some central point. It's rewriting the rules of where and how things exist altogether. Here's something that will bend your perception of reality. Everything we can see, touch, and measure in the universe, from the tiniest grain of sand to the largest supercluster of galaxies, makes up less than 5% of what's actually out there. The rest, a cosmic phantom called dark matter. Picture this, you're floating in space, watching galaxies spin like glowing pinwheels, but something's off. The stars on the outer edges are whipping around just as fast as those near the center, defying the laws of gravity as we know them. It's as if an invisible hand is holding them in place. That hand is dark matter. Scientists first caught onto this mystery in the 1930s when astronomer Fritz Zwicky noticed that galaxies in the Coma cluster were moving too fast to stay together under their visible gravity alone. He called it Dunkel Materie, dark matter, and though his peers dismissed it at the time, we now know he was onto something monumental. Here's how we detect what we can't see. Imagine walking into a pitch-black room and feeling the air swirl around you as unseen objects move past. Dark matter works the same way. Its gravity tugs on stars and bends light like a cosmic lens, betraying its presence without ever showing its face. But what is it? That's the trillion-dollar question. It's not made of atoms, it doesn't emit or absorb light, and it passes through ordinary matter like a ghost. Leading theories suggest it could be a sea of exotic particles left over from the Big Bang, or even an entire shadow universe with its own invisible physics. Underground labs hunt for it with vats of liquid xenon, while particle colliders try to create it in miniature explosions of energy. So far, no dice. The wildest part, dark matter isn't just holding galaxies together. It sculpted the universe's very structure. Without it, gravity wouldn't have had enough clumpiness in the early cosmos to pull together the first stars and galaxies. We owe our existence to this invisible scaffold, yet we still don't know what it's made of. It's like living in a house where the walls and floors are made of something you can't see, touch, or describe. You just know they're there because the roof hasn't caved in. Every time we think we're close to cracking the mystery, dark matter slips through our fingers again. But that's the thrill of cosmic detective work. Sometimes the biggest truths are hiding in plain sight, or in this case, in the darkest corners of space. Let's talk about nothing literally. If you scooped up a handful of the universe, what would you actually be holding? Here's the staggering truth: mostly emptiness. The atoms that make up everything, your body, the stars, even the screen you're staring at, are overwhelmingly hollow. Picture an atom as a cathedral. The nucleus, a single grain of sand at the center, would be orbited by electrons whirling like dust motes near the ceiling. The rest pure void. Now zoom out to the cosmos, and this emptiness becomes almost unimaginable. The average distance between stars in our galaxy is about 4 light-years. That's 24 trillion miles of near nothingness. To grasp that scale, imagine shrinking our solar system down to a coffee cup. On that scale, the next star over would be another cup sitting in New York City while you're in Los Angeles. But it gets stranger. Galaxies themselves float in even vaster deserts called cosmic voids, regions so empty they could fit thousands of Milky Ways with room to spare. The Boötes Void, one of the largest known, spans 330 million light-years and contains barely 60 galaxies. If the universe were a beach, matter would be a few scattered grains of sand lost in endless dunes of dark, silent space. Why does this matter? Because it reshapes how we see reality. That solid table beneath your hands, it's really a cloud of particles never quite touching, held together by forces we can't see. And the night sky, those glittering stars we romanticize, are actually lonely beacons separated by abysses so vast, light itself takes generations to cross them. Here's the kicker: this emptiness is what allows the universe to exist. If atoms were packed tightly, gravity would have crushed everything into black holes long ago. Instead, the void gives galaxies room to spin, stars space to burn, and just maybe life a chance to emerge in the quiet corners of an almost empty cosmos. So next time you feel small, remember, you're not just standing on a planet, you're floating in the grandest emptiness there is. Time isn't the constant, unchanging force we experience in our daily lives. It's more like a river, bending and twisting under the weight of the universe itself. Nowhere is this more extreme than near a black hole, where gravity warps time so severely that minutes here could equal years elsewhere. This isn't science fiction, it's Einstein's theory of relativity in action. Picture a trampoline with a bowling ball in the center, creating a deep well. If you roll marbles near the edge, they'll spiral inward slowly, but drop one right next to the bowling ball and it'll whip around at dizzying speeds. Space-time works the same way. A black hole's gravity is so intense, it doesn't just bend space, it stretches time itself. The closer you get, the slower your clock ticks compared to someone watching from afar. This effect, called gravitational time dilation, was famously dramatized in Interstellar when the crew lands on Miller's planet, orbiting the black hole Gargantua. For every hour they spend on the surface, 7 years pass back on Earth. While the movie took creative liberties, the science behind it is shockingly real. Near a supermassive black hole, time wouldn't just slow down, it would nearly grind to a halt from an outsider's perspective. Here's why this happens. Imagine two clocks, one on Earth, another near a black hole. Both tick perfectly, but the black hole's gravity pulls so hard on space-time that light from the distant clock has to climb out of a deeper well, making each second stretch longer when viewed from outside. Astronomers have even measured this effect around Earth. GPS satellites orbiting where gravity is slightly weaker tick faster than ground clocks by microseconds each day. Without corrections, your phone's navigation would drift off course in minutes, but black holes take this to the extreme. If you could hover near the event horizon, you'd watch the rest of the universe speed up like a fast-forwarded movie. Stars would flare and die in seconds, galaxies would swirl like storm clouds, and cosmic history would unfold before your eyes. Of course, you'd also be stretched into spaghetti by tidal forces long before that, but the point stands: time isn't just a measurement. It's a fabric, and gravity is the hand that sculpts it. Einstein's revelation rewrote our understanding of reality, proving that time is relative. Your experience of it depends entirely on where you are and how fast you're moving. So next time you glance at a clock, remember, it's not just counting seconds, it's telling the story of space itself bending around you. The night sky isn't just dotted with stars, it's drowning in them. Picture every grain of sand on every beach, every desert dune, every speck in the ocean floor. Now multiply that number by 10. That's how many stars twirl through the cosmos, an estimated 1 septillion, or 10 to the power of 24. Wrap your mind around this. If you tried to count them all at a rate of 1 per second, you'd still be counting 30 trillion years from now. But why does this number matter? Because it reshapes the odds in humanity's oldest question. Are we alone? Statistically, the answer tilts toward almost certainly not. Consider that for every grain of sand on Earth, there are roughly 10 stars out there. And orbiting those stars, planets so many that astronomers now estimate each star hosts at least one on average. That means there could be more planets in the universe than all the grains of sand on every beach that's ever existed. Suddenly, the idea that life only sparked here feels like betting on a single lottery ticket in an ocean of winning numbers. Here's where it gets wild. Even if the chance of life emerging on any given planet were astronomically low, say, 1 in a trillion, the sheer scale of the cosmos still leaves room for millions, even billions, of life-bearing worlds. It's like flipping a coin a septillion times. Even with terrible odds, you'd still expect a staggering number of heads. The kicker: we've barely begun to search. Less than 1% of our own galaxy has been scanned for signs of life, and already telescopes have spotted planets with water vapor in their atmospheres, moons with subsurface oceans, and organic molecules swirling in distant nebulae. Each discovery narrows the gap between science fiction and science fact. So when you stand on a beach letting sand slip through your fingers, remember, you're holding a cosmic census. Those tiny grains are a whisper of the universe's unimaginable vastness. And if the stars outnumber them by such an impossible margin, what else might be waiting in the dark? The numbers don't just hint at possibility, they shout it. The moon isn't just hanging in the sky, it's slowly escaping. Right now, as you read this, our closest cosmic companion is creeping away from Earth at roughly the same speed your fingernails grow, 3.8 centimeters every year. It might not sound like much, but over time, this tiny drift adds up to something monumental. Here's why it's happening. Earth's gravity locks the moon in orbit, but the moon's own gravity tugs back, especially on our oceans. Those tidal bulges, the rise and fall of the seas, actually stretch ahead of the moon slightly due to Earth's rotation. This creates a gravitational tug of war, with the moon pulling the bulges forward, and the bulges, in turn, dragging the moon just a little faster in its orbit. Physics demands that when an orbiting object speeds up, it spirals outward. So, bit by bit, the moon is being pushed away like a child on a swing, getting higher with every push. But what does this mean for us? For starters, eclipses will become a relic of the past. Total solar eclipses happen because, by sheer cosmic coincidence, the moon and sun appear the same size in our sky. As the moon retreats, it'll seem smaller, eventually no longer able to fully cover the sun. In about 600 million years, the last true total eclipse will occur, a bittersweet curtain call for one of nature's most stunning displays. The moon's departure also slows Earth's spin like an ice skater extending their arms. Billions of years from now, a day on Earth could stretch to 47 hours, with the moon so distant it would appear as just another faint star. Some models even suggest Earth and moon might become tidally locked, forever showing each other the same face, like distant dancers frozen mid-step. Yet this drift isn't just a slow goodbye, it's a reminder of how dynamic our cosmic neighborhood really is. The moon was once 10 times closer, making tides 1,000 times higher and turning coastlines into raging whirlpools. Its gravitational grip helped stabilize Earth's tilt, preventing wild climate swings that could have snuffed out life before it began. So while we're losing our lunar neighbor inch by inch, we're also witnessing the delicate ballet that's shaped our planet's history and will keep rewriting it long after we're gone. Deep space might seem like the ultimate deep freeze, but the coldest place we've ever found isn't light years away. It's right here in a lab. The Boomerang Nebula, a ghostly cloud of gas 3,000 light-years from Earth, holds the natural record at just 1 degree Kelvin above absolute zero. That's colder than the cosmic microwave background, the leftover glow from the Big Bang itself. But scientists have outdone even the void of space, chilling atoms to temperatures 1 billion times closer to absolute zero than the nebula. How? Picture a refrigerator designed by a physicist with a taste for extremes. First, lasers are used to slow atoms down because temperature is just a measure of motion. Blast a cloud of rubidium atoms with carefully tuned lasers from all directions, and they'll act like they're pushing through molasses, losing energy until they're barely moving at all. Next comes evaporative cooling, where the fastest atoms are skimmed off like foam from a latte, leaving only the slowest, coldest ones behind. The result: temperatures within a hair's breadth of absolute zero, where atoms stop behaving like particles and start acting like waves, merging into a bizarre quantum state called a Bose-Einstein condensate. Here's where it gets surreal. At these temperatures, matter doesn't just get cold, it starts breaking the rules. Liquid helium flows uphill, superconductors levitate magnets indefinitely, and atoms sync up like perfectly choreographed dancers. The record sits at 38 trillionths of a degree above absolute zero, a number so small it's like comparing the width of a human hair to the distance across our galaxy. Why push the limits like this? Because ultra-cold labs are windows into the quantum world. They let us simulate conditions near black holes, test theories about dark energy, and even craft materials that could revolutionize computing. The Boomerang Nebula may wear nature's crown for now, but in the race to the bottom of the thermometer, human ingenuity is rewriting what we thought was possible, one frozen atom at a time. The sunlight warming your skin right now isn't new, it's 8 minutes old. That beam traveled 93 million miles at the universe's speed limit to reach you, meaning if the sun vanished this instant, we wouldn't just carry on blissfully unaware. Earth would continue orbiting nothing for 8 minutes before the sky went dark and gravity let go. Here's how it works. Light moves fast, but space is vast. Even at 300,000 kilometers per second, crossing the gulf between Earth and the sun takes time. Imagine shouting across a canyon. The sound doesn't reach the other side instantly. Light behaves the same way, creating a cosmic delay that turns our sky into a time machine. When you gaze at the star Sirius, you're seeing it as it was 8.5 years ago. The Andromeda Galaxy, that shimmer, is 2.5 million years out of date. This delay becomes haunting when applied to our own star. Solar flares erupting right now won't affect Earth until 8 minutes later, enough time for auroras to dance or satellites to fry with no advanced warning. It's like watching a pre-recorded disaster with no power to stop it. Space agencies actually monitor the sun's activity with a built-in countdown, knowing every alert comes with an unavoidable lag. But this cosmic voicemail system has an upside. Those distant stars we observe, their light carries chemical fingerprints from ancient eras, letting astronomers read the universe's history like pages in a book. A star's red shift tells us how fast it fled during the Big Bang, while supernova explosions captured by telescopes may have actually occurred before Earth formed. Even the Hubble Deep Field image, showing thousands of galaxies, is a mosaic of light that left its sources when single-celled life ruled our planet. So next time you feel sunlight on your face, remember, you're not just standing under a star, you're touching a message from the past sent across space at a speed that makes everything we see an echo of what once was. The night sky isn't a snapshot, it's a scrapbook of the cosmos with every twinkle on a different page of time. And here's the mind-bending twist. This same principle means aliens observing Earth right now from distant stars wouldn't see smartphones or skyscrapers. The closest star system, Alpha Centauri, gets a 4-year-old broadcast of our planet dinosaurs roaming if they're looking from 65 million light-years away. It makes you wonder what scenes are sailing through the void right now, carried on light beams we'll never catch. There's a place in the universe so empty, so utterly devoid of anything that astronomers call it the Great Nothing. The Boötes void stretches 330 million light-years across a staggering bubble of near-perfect emptiness that defies everything we know about how the cosmos should look. To grasp how bizarre this is, imagine a ballroom packed with people, except for one perfect sphere where not a single soul stands for miles. Now scale that up to cosmic proportions and you've got the Boötes void. This cosmic ghost town sits 700 million light-years from Earth and contains just 60 galaxies, about 1/10 the number you'd expect in a region that size. If our Milky Way were stranded here, our nearest galactic neighbor would be so far away, its light would take millions of years to reach us. The void scale is almost incomprehensible. You could fit 2,000 Milky Ways end-to-end across it with room to spare. Even crazier, the entire observable universe is only about 93 billion light-years wide, making this void a yawning chasm that occupies a significant fraction of everything we can see. So how did this cosmic desert form? One theory suggests it's the aftermath of ancient collisions between smaller voids like soap bubbles merging into one giant emptiness. Another idea points to dark energy, the mysterious force accelerating the universe's expansion, potentially stretching certain regions into barren wastelands. But the most haunting possibility, the Boötes void, might be a relic of inflation, a frozen scar from the universe's first trillionth of a second, when space itself expanded faster than light, leaving behind pockets of nothingness. Here's what makes it even stranger. Voids like this aren't just empty space, they actively reshape the universe. Galaxies at the edges are being hurled outward by the void's gravitational repulsion, a phenomenon called the integrated Sachs-Wolf effect. It's as if the cosmos is allergic to emptiness, pushing matter away like two magnets with the same polarity. The Boötes void might also hold clues to dark matter's nature, since its gravitational pull or lack thereof affects how galaxies move around it. Yet for all its emptiness, the Boötes void isn't completely barren. Those 60-odd galaxies drifting inside are like lone sailors on an endless ocean, isolated in a way we can hardly fathom. Some are void galaxies, starved of interstellar gas and evolving differently than their cluster-dwelling cousins. Studying them is like finding life in the Atacama Desert, proof that even the harshest environments can harbor something extraordinary. The void challenges our assumptions about the universe's structure. We used to picture galaxies spread evenly like raisins in a cake, but the cosmos is more like Swiss cheese, full of holes we're only beginning to map. And the Boötes void isn't alone. The universe is littered with these empty realms, some even larger. They remind us that for all its splendor, the cosmos is fundamentally uneven, unpredictable, and far stranger than any model can capture. So the next time you feel insignificant under a starry sky, remember, even the vastness we see is just the stuff that didn't get swept away by the universe's emptiness. The Boötes void isn't just a curiosity, it's a humbling glimpse into how much of existence might simply be nothing at all. Imagine taking Mount Everest, crushing it down to the size of a sugar cube, and discovering it's still not dense enough to match a neutron star. These cosmic leftovers from supernova explosions are so unimaginably dense. A single teaspoon of their material would weigh 1 billion tons on Earth, as much as all the cars in the world combined. That's not just heavy, that's gravity warping reality itself. When a massive star dies in a supernova, its core collapses under its own weight. Protons and electrons get squeezed together so violently they merge into neutrons, packing the mass of 1.4 suns into a sphere no wider than Manhattan. The result, a neutron star, nature's ultimate pressure cooker. Standing on its surface, if you could survive the experience, would subject you to gravity 100 billion times stronger than Earth. Light itself bends around these objects, creating optical illusions where you could see the back of your own head if you looked straight ahead. But the strangeness doesn't stop there. Neutron stars spin faster than kitchen blenders, some rotating 700 times per second. Picture this, a star heavier than our sun, spinning so fast its equator moves at 1/4 the speed of light. That centrifugal force should tear it apart, except the star's gravity is so intense, not even atoms can escape being crushed into submission. These rapid spinners, called pulsars, beam radiation like cosmic lighthouses, creating flashes so regular they rival atomic clocks in precision. Then there are magnetars, neutron stars with magnetic fields 1 quadrillion times stronger than Earth's. Get within 600 miles of one, and those fields would scramble your atoms, pulling the iron from your blood like a cosmic magnet. Their occasional starquakes release energy equivalent to 1 billion hydrogen bombs, making them some of the most volatile objects in existence. What's truly humbling is how these stellar zombies shape the universe. Colliding neutron stars forge gold and platinum in their wake, sprinkling precious metals across galaxies. Their extreme conditions let physicists test Einstein's theories in ways no Earth lab could replicate. And when two neutron stars spiral together, they don't just explode, they send ripples through space-time itself, vibrations we've now detected as gravitational waves. So next time you stir sugar into your coffee, consider this. Somewhere out there, a single speck of neutron star material is outweighing mountains, bending the fabric of space, and reminding us that the universe's most astonishing wonders often come in the smallest, most extreme packages. If you could take a deep breath in the depths of space, which of course you can't, you might catch a whiff of something bizarrely familiar. Floating in a giant gas cloud near the center of our galaxy, astronomers discovered a molecule called ethyl formate, the very same chemical that gives raspberries their sweet scent and rum its distinct aroma. That's right, the universe, in at least one corner, smells like a cosmic cocktail bar. Now, before you imagine astronauts floating through berry-scented nebulae, here's the catch. Space itself is a near-perfect vacuum, meaning there's no air to carry smells to our noses. Those tantalizing raspberry and drum notes would remain forever out of reach, locked in an interstellar cloud 25,000 light-years away. But that doesn't make the discovery any less fascinating. Scientists stumbled onto this celestial fragrance while studying Sagittarius B2, a massive star-forming region teeming with complex molecules. Using radio telescopes, they detected the chemical fingerprints of ethyl formate swirling in the cloud, a molecule so large and intricate, its presence in space was once thought improbable. It's not alone either. Over 200 different molecules have been identified in similar clouds, from sugary glycolaldehyde to vinegar like acetic acid. Why does this matter? Because these molecules are the building blocks of life, or at least the precursors to the chemistry that makes life possible. The same processes that brew raspberry-scented compounds in space could have seeded Earth with organic materials billions of years ago. Some scientists even speculate that the ingredients for DNA might have hitched a ride on comets or meteorites, raining down on our planet in its infancy. But here's the twist. While ethyl formate might smell delightful in small doses, concentrated clouds of it would likely overwhelm your senses with an alcohol-like punch. And that's assuming you could survive the surrounding environment. Sagittarius B2 is a cauldron of radiation, extreme temperatures, and chaotic stellar winds. So the next time you bite into a raspberry or sip a cocktail, consider this. Somewhere out there, on a scale we can barely fathom, the universe is mixing its own version of those flavors in the dark. It's a reminder that the cosmos isn't just a sight to behold. It's a recipe, endlessly combining atoms into the familiar and the strange, all without us ever catching a single whiff. Mercury might look like a lifeless rock from afar, but beneath its sun-scorched surface, the planet is literally caving in on itself. While Earth's tectonic plates drift and collide in slow motion, Mercury is performing a cosmic vanishing act, shrinking as its molten core cools and solidifies. Over billions of years, this process has sculpted towering cliffs, some stretching for hundreds of miles and rising over a mile high, like wrinkles on a raisin left out in the solar oven. Here's why this happens. When Mercury formed, it was a seething ball of molten metal and rock. But unlike Earth, with its thick mantle insulating the core, Mercury's small size, only slightly larger than our moon, means it loses heat rapidly. As the core cools, it contracts, causing the planet's rigid outer shell to buckle and fracture. These cracks aren't like gentle folds in a blanket. They're dramatic scarps, some with sheer drops that would dwarf the Grand Canyon. The most famous, Beagle Roops, is a towering fault line that snakes across the surface like a colossal stitch holding the planet together. What's fascinating is how this contrasts with Earth. Our planet's core remains molten thanks to radioactive decay and the insulating layers above, keeping the engine of plate tectonics running. Mercury, though, it's a one-plate world with no tectonic activity to relieve the pressure, so when the core shrinks, the entire crust has no choice but to crumple. It's like comparing a grape Earth with its flexible skin to a walnut Mercury, brittle and cracking under pressure. This shrinkage isn't just ancient history, it's ongoing. NASA Messenger spacecraft spotted fresh-looking scarps, suggesting Mercury is still contracting today. If you could stand on its surface, you might feel the ground beneath you groaning as the planet tightens its belt, millimeter by millimeter. But here's the real kicker. Mercury's slow collapse offers clues about other rocky worlds. Exoplanets smaller than Earth might follow the same fate, their surfaces buckling under cooling cores long before life could take hold. So while Mercury's cliffs make it a geological oddball, they also remind us that size matters in the cosmos. Too small, and a planet's fiery heart turns to stone, leaving behind a landscape frozen in the act of collapse. Venus isn't just another planet, it's the solar system's ultimate rebel. While every other planet spins counterclockwise when viewed from above, Venus flips the script, rotating clockwise in what astronomers call retrograde rotation. Imagine a clock running backward or a vinyl record spinning the wrong way. That's Venus, defying the norm with a slow, stubborn twist that takes longer to complete a single day than it does to circle the sun. So how did this cosmic maverick break the mold? One leading theory points to violence in the early solar system. Picture this: 4.5 billion years ago, a protoplanet the size of Mars slams into Venus at just the right angle, hitting it like a celestial pool cue. The impact could have sent Venus spinning backward or even knocked it upside down entirely. Over time, tidal forces from the Sun's gravity likely slowed its rotation to the sluggish pace we see today. Evidence for this comes from Venus' lack of a moon, another possible casualty of that apocalyptic collision. But there's another twist. Venus doesn't just spin backward, it does so agonizingly slowly. A single Venusian day lasts 243 Earth days, making its day longer than its year, which zips by in just 225 Earth days. If you stood on its surface, ignoring the crushing pressure and acid rain, you'd witness a sun that rises in the west, sets in the east, and takes months to cross the sky. The strangeness doesn't stop there. Venus' thick atmosphere actually super-rotates, whipping around the planet every 4 Earth days while the surface crawls along beneath it. It's like a runaway carousel spinning above a snail's pace parade. This disconnect between atmosphere and ground creates hurricane-force winds and storms that never cease, wrapping the planet in a perpetual shroud of chaos. What makes Venus' backward spin even more puzzling is how rare it is. Uranus also bucks the trend, but it rolls on its side like a barrel, possibly tipped over by multiple collisions. Venus alone chose the full opposite direction, making it the solar system's standout contrarian. Some scientists argue tidal forces and atmospheric drag alone could have reversed its spin, no collision required. Others suggest gravitational tugs from other planets during the solar system's chaotic youth might have flipped it. One thing's certain, Venus' peculiar spin shapes its extreme environment. That slow rotation means no magnetic field to shield it from solar winds, leaving it vulnerable to radiation. The lack of day-night temperature variations combined with a runaway greenhouse effect turns its surface into a furnace hot enough to melt lead. Even its clouds are laced with sulfuric acid, creating a haze that reflects sunlight so brilliantly, Venus outshines every star in our sky except the Sun. So while Mars gets all the attention for potential life, Venus quietly spins its own tale of cosmic defiance. It's a reminder that in our solar system, the rules are more like suggestions, and sometimes the most fascinating worlds are the ones that refuse to follow them. Jupiter's Great Red Spot isn't just a storm, it's a monster that's been raging longer than modern civilization has existed. This swirling crimson tempest is so vast you could drop 3 Earths side by side inside it and still have room to spare. For at least 400 years, possibly longer, this hurricane has churned with winds screaming at 400 miles per hour, spinning counter-clockwise like a cosmic blender set to obliterate. What keeps this beast alive? Jupiter's atmosphere is a laboratory of extremes. Unlike Earth, where storms feed off ocean heat and eventually fizzle over land, Jupiter has no surface to break the fury, just an endless abyss of hydrogen and helium. The Great Red Spot sits between 2 jet streams racing in opposite directions, acting like a pair of conveyor belts that keep the storm spinning. It's also powered by heat rising from Jupiter's core, turning the planet's atmosphere into a pressure cooker of chaos. But here's the twist, this icon of cosmic violence is slowly vanishing. In the late 1800s, the storm was wide enough to swallow 4 Earths. By the time Voyager flew past in 1979, it could fit 3. Today, barely 1.5. Astronomers debate why. Some blame changes in Jupiter's wind patterns, while others suspect mysterious energy losses deep within the storm itself. If the shrinking continues, the Great Red Spot could fade into oblivion within our lifetimes, leaving Jupiter's face unrecognizable to future generations. Yet even in its decline, the storm astounds. Juno spacecraft measurements revealed its roots plunged 200 miles into Jupiter's atmosphere, far deeper than expected. That depth might explain its longevity, anchoring it like a spinning top wedged into the planet's guts, and its color, likely a cocktail of chemicals like ammonium hydrosulfide, turned crimson by ultraviolet light or cosmic rays bombarding Jupiter's clouds. The storm's possible demise raises bigger questions. Is this part of a natural cycle where Jupiter grows new storms as old ones fade? Or are we witnessing the end of an era, a cosmic landmark vanishing before our eyes? Either way, the Great Red Spot reminds us that even the mightiest forces in the universe are temporary, just a fleeting swirl in the endless dance of the cosmos. Saturn's iconic rings, those dazzling bands of ice and dust that have inspired astronomers for centuries, are vanishing right before our eyes. Imagine a celestial waterfall where countless icy particles are slowly but surely raining down onto the planet's surface. This isn't poetic exaggeration, it's a real phenomenon called ring rain, and it means Saturn's most famous feature is on borrowed time. In roughly 300 million years, those breathtaking loops could be gone forever, leaving the gas giant naked to the universe. The rings are made up of trillions of chunks of water ice, some as small as dust grains, others as big as houses. But Saturn's gravity is relentless, pulling this material downward in a continuous shower. Scientists first noticed the effect when spacecraft detected dark bands in Saturn's upper atmosphere striations caused by falling ring material interacting with the planet's magnetic field. The rings are losing an estimated 10 to 45,000 pounds of material every second. At that rate, they might only last another few hundred million years, a blink in cosmic terms. What makes this even more fascinating is the timing. Saturn's rings are relatively young, possibly forming just 100 million years ago, meaning dinosaurs might have walked Earth before the rings even existed. Now we're witnessing their golden age, a fleeting window where Saturn wears its jewelry in full display. Future civilizations might gaze at Saturn through telescopes and see nothing but a blank yellow orb, wondering if the rings were ever real. The rings aren't just passively crumbling, they're fighting a losing battle with solar radiation. Sunlight charges the icy particles, making them susceptible to Saturn's magnetic field, which then drags them into the atmosphere like cosmic lint. The innermost rings are vanishing fastest, thinning at a rate that suggests they could disappear within the next 100 million years. The outer rings might linger longer, but their fate is sealed. This slow-motion demolition gives astronomers a rare opportunity. By studying the rate of decay, they can piece together the rings' origins. Some theories suggest they're the shredded remains of a moon torn apart by Saturn's gravity, while others propose they're leftover debris from the solar system's formation. Whatever their source, their impermanence reminds us that even the most breathtaking cosmic sights are transient. So the next time you see an image of Saturn's rings, remember, you're looking at a masterpiece in its prime, a spectacle that future generations might only know from history books. The universe doesn't stand still, it's always changing, always evolving, and right now, we're lucky enough to witness one of its most dazzling acts before the curtain falls. Uranus doesn't just orbit the Sun, it practically rolls around it like a wayward bowling ball. While most planets spin like tops as they circle our star, Uranus is tipped over on its side with an extreme 98-degree axial tilt, making its poles face the Sun directly for stretches of its 84-year orbit. Picture this, during its long summer, one pole bakes under perpetual daylight for 21 Earth years, while the other plunges into an endless freezing night. Then, as Uranus continues its slow roll, the roles reverse like a cosmic rotisserie stuck on a bizarre cycle. What could have knocked a planet so completely off kilter? The leading theory points to a cataclysmic collision early in the solar system's history. Imagine a protoplanet, perhaps twice the size of Earth, slamming into Uranus with such force that it sent the planet spinning sideways. The impact might have been so violent, it could also explain why Uranus' magnetic field is wildly off-center, tilted 60 degrees from its axis and offset by a third of the planet's radius. It's as if the planet's internal compass got thrown into chaos along with its rotation. But not all scientists are convinced a single impact tells the full story. Some suggest gravitational chaos played a role. Tugs from Saturn and Jupiter during the solar system's turbulent, youth could have gradually pulled Uranus into its sideways state. Think of it like a game of cosmic tug-of-war, where the combined forces of giant planets nudged Uranus over time. There's even a wilder idea. Uranus might have once had a massive moon whose gravitational influence destabilized its spin, only for that moon to be ejected or destroyed, leaving the planet forever tilted. The consequences of this tilt are stranger than fiction. Uranus' magnetosphere wobbles asymmetrically as it rotates, creating a magnetic tail that spirals like a corkscrew through space. Its seasons are equally bizarre. While Earth's poles take turns facing the Sun in a predictable rhythm, Uranus' extreme tilt means entire hemispheres spend decades in sunlight or darkness, with the equator plunged into frigid shadow. When Voyager 2 flew by in 1986, it caught Uranus in the middle of its blandest season, showing a nearly featureless blue-green ball. But recent observations reveal storms and cloud bands flaring up as sunlight finally reaches long darkened regions, like a planet waking from hibernation. Here's the real kicker: Uranus isn't alone in its oddity. Venus spins backward, and Pluto's axis tilts even more dramatically at 120 degrees. But Uranus stands out because its tilt affects everything: its weather, its magnetism, even the way it interacts with the solar wind. It's a reminder that the solar system isn't a neat, orderly clockwork. It's a collection of survivors, each bearing the scars of ancient chaos. And Uranus, rolling through space with its poles leading the way, might be the most dramatic testament to that violence we've ever found. Somewhere in the constellation Cancer, a planet shimmers with the promise of impossible riches, not gold or silver, but something far more exotic. Meet 55 Cancri E, a world so dense with carbon that its interior may be one gigantic diamond, floating in the void like a cosmic jewel. This isn't science fiction, it's astrophysics at its most dazzling. About twice Earth size, but nearly 8 times as massive, 55 Cancri E orbits so close to its star that its year lasts just 18 hours. Surface temperatures soar above 4,000 degrees Fahrenheit, hot enough to vaporize rock and turn its carbon-rich crust into a bubbling ocean of molten graphite. But dive deeper and the real magic begins. The crushing pressure, millions of times stronger than Earth's atmosphere, could compress that carbon into crystalline perfection, forging a diamond layer hundreds of miles thick. How does a planet become a gemstone? It starts with chemistry. Most rocky planets, like Earth, form from silicon and oxygen. But 55 Cancri E was born in a system unusually rich in carbon, the same element that makes up diamonds. Think of it like baking a cake. If Earth's recipe uses flour, this planet swapped it for pure sugar. Under extreme heat and pressure, that carbon doesn't just harden, it transforms, stacking its atoms into the rigid lattice structure of diamond. But don't pack your mining gear just yet. Even if you could survive the surface, a seething, pitch-black landscape where the air might be vaporized rock, the diamond itself would be unattainable. It's not a glittering crust waiting to be chipped away. It's a super-dense mantle, possibly mixed with other exotic forms of carbon, like liquid metallic hydrogen or even layers of compressed graphene. The planet's composition raises wild questions. Could there be diamond-rich worlds with even more extreme structures? Some models suggest planets like this might have cores of liquid carbon, where pressures are so intense that diamonds melt like ice cream on a summer day. Others speculate about carbon planets with diamond bergs floating on seas of molten hydrocarbons. 55 Cancri E isn't just a cosmic curiosity. It's a window into how alien chemistry can reshape entire worlds. While Earth's carbon is locked in life and limestone, this planet's carbon became its bedrock, its sky, its very essence. It's a reminder that the universe doesn't just deal in rock and gas sometimes, it crafts wonders beyond our greediest dreams. And here's the twist: 55 Cancri E might not be alone. With trillions of planets in the galaxy, how many other diamond worlds are waiting to be found? Each one would rewrite what we thought possible, proving that even the rarest treasures on Earth might be commonplace in the cosmos. So next time you admire a diamond ring, remember, somewhere out there, an entire planet is putting every jewelry store to shame. At the heart of our galaxy, hidden behind thick clouds of cosmic dust, lies a monster, a supermassive black hole named Sagittarius, a star. This gravitational behemoth packs the mass of 4 million suns into a space smaller than our solar system, bending the very fabric of reality around it. But despite its terrifying power, it's not the devouring beast you might imagine. In fact, it's strangely quiet, a sleeping giant that barely sips on the stars around it. How does something so massive stay so calm? Black holes like Sagittarius, a star, aren't cosmic vacuum cleaners. They only consume matter that strays too close. Right now, it's dining on what astronomers call a starvation diet, with only wisps of gas and the occasional unlucky star falling into its grasp. Most of the time, these meals are so sparse that the black hole's surroundings glow faintly, like embers in a dying fire. But when it does feed, the galaxy's core erupts in bursts of X-rays and radio waves, flashes of violence that hint at the power lurking beneath the quiet. Yet Sagittarius, a star's influence stretches far beyond its event horizon. Its gravity is the anchor around which the entire Milky Way spins, holding hundreds of billions of stars in a vast, swirling dance. Stars near the galactic center whip around it at thousands of miles per second, their orbits tracing wild ellipses like moths circling a flame. Some, like the star S2, come so close they complete an orbit in just 16 years, a blink in cosmic terms. Their frenzied paths are proof of the black hole's grip, a gravitational signature no telescope can ignore. What's truly baffling is how small Sagittarius, a star, seems compared to other supermassive black holes. In distant galaxies, some of these titans weigh in at tens of billions of solar masses, guzzling gas so voraciously they outshine every star around them. Ours, by contrast, is almost docile, a reminder that not all galactic cores are raging infernos. Some, like ours, prefer the quiet life, shaping their galaxies through subtle tugs rather than violent feasts. But don't let its calm fool you. Sagittarius, a star, has a violent past. Buried in the light echoes of nearby gas clouds are clues to ancient eruptions, times when it flared with the energy of a million supernova, likely after swallowing a star hole or a massive gas cloud. Even now, astronomers watch for flickers in its glow, signs that something might be falling into the dark. And here's the twist: this sleeping giant might be the key to understanding how galaxies are born. Every large galaxy we've found seems to have a supermassive black hole at its core, a partnership so consistent it can't be coincidence. Did the black hole shape the galaxy, or did the galaxy feed the black hole? It's a cosmic chicken and egg puzzle that Sagittarius, a star, is helping us solve, one quiet orbit at a time. So the next time you look toward the constellation Sagittarius, remember, you're peering toward an invisible colossus, a force so immense it holds the Milky Way together without making a sound. It's not just a black hole, it's the silent architect of our galactic home. Right now, the Andromeda Galaxy is racing toward us at 250,000 miles per hour, a head-on collision course set for 4 billion years from now. But here's the cosmic irony: when these two titans finally meet, the stars within them won't so much as bump into each other. That's because galaxies are mostly empty space, their stars scattered so far apart that direct hits are almost impossible. Imagine two swarms of bees flying through each other in slow motion, where each bee is miles from its nearest neighbor. That's how sparse galaxies really are. When Andromeda and the Milky Way merge, the real drama won't be stellar smash-ups. It'll be gravity's grand rearrangement. The two black holes at their cores will spiral inward, locked in a gravitational dance until they finally merge, sending ripples through space-time. Stars will be flung into wild new orbits, some hurled outward into the cosmic void while others get reeled in toward the chaotic center. gas clouds will collide, igniting bursts of new star formation so intense the night sky of any surviving planets would glow with young blue-white stars. Computer simulations paint a mesmerizing picture, a ballet of destruction and rebirth. At first, the galaxies will pass through each other like ghosts, their gravity distorting their shapes into long, luminous tidal tails. Then, like pendulums, they'll swing back, drawn together again and again until their structures blur into a single, elliptical galaxy astronomers have nicknamed Milkdromda. The entire process will take billions of years, unfolding so slowly that any hypothetical future civilization might not even notice the change in their lifetime. What's truly humbling is how little danger this poses to stars and planets. The Sun, for instance, will likely be tossed into a new orbit far from the galactic core, but the odds of another star coming close enough to disturb our solar system are vanishingly small. Even in the densest regions of the merging galaxies, stars will miss each other by light years. The real threat isn't collisions, it's the violent reshuffling of gas and dust that could trigger supernova or gamma-ray bursts near inhabited worlds. Yet for all the chaos, there's beauty in this inevitability. The merger will stitch together two histories: Andromeda's ancient stars, some nearly as old as the universe itself, mingling with the Milky Way's younger, metal-rich population. Their combined light will create a night sky unlike anything Earth has ever seen, a glittering hybrid of two cosmic lineages. And long after the merger finishes, the new galaxy stars will carry the gravitational memory of this event in their orbits, like fossils of a collision written in motion. So while we think of galaxies as crowded cities of stars, they're more like vast, lonely archipelagos, islands in a sea of nothingness, drifting close enough to reshape each other without ever truly touching. The universe's greatest mergers aren't crashes. They're rearrangements, slow dances where gravity does the work while stars barely notice they've changed neighborhoods. The universe isn't just expanding, it's doing so at an ever-increasing speed, as if some invisible force is pressing harder and harder on the gas pedal of reality itself. This discovery, which won the Nobel Prize in Physics in 2011, upended everything we thought we knew about cosmic fate. Instead of gravity gradually slowing the expansion, as scientists assumed for decades, galaxies are fleeing from one another faster today than they were billions of years ago. And the culprit behind this cosmic acceleration, a mysterious something we call dark energy. Picture this: you throw a ball into the air, and instead of slowing down as it climbs, it rockets away faster and faster, defying gravity entirely. That's precisely what dark energy is doing to the fabric of space. It makes up roughly 68% of the universe's total energy, yet we have no idea what it actually is. Some theories suggest it's a property of space itself, a cosmological constant Einstein once proposed, then dismissed as his greatest blunder. Others speculate it's a dynamic field that changes over time, or even evidence of extra dimensions leaking gravity into our universe. The implications are staggering. If dark energy keeps strengthening, it could lead to what cosmologists call the Big Freeze, a future where space stretches so rapidly that galaxies, stars, and eventually atoms are torn apart. First, distant galaxies would vanish from view as the space between us expands faster than light can cross it. Then, over trillions of years, even the Milky Way stars would fade into isolation, their light stretched into useless infrared whispers. Eventually, the very fabric of matter might unravel in a catastrophic Big Rip, where not even atomic bonds can resist the expansion's pull. But there's another, eerier possibility. Dark energy might not be constant at all. What if it weakens over time, allowing gravity to regain control? In that scenario, the universe could reverse course in a big crunch, collapsing back into a singularity, perhaps birthing a new universe in a cyclical rebirth. Or dark energy might fluctuate unpredictably, creating pockets of space that collapse while others accelerate away eternally. Here's the twist: we might never know for sure. The most distant light we can see, the cosmic microwave background, shows the universe's state nearly 14 billion years ago. The fate playing out today in the voids between galaxies is invisible to us, like trying to predict a hurricane's path by studying ripples in a pond long after the wind has changed. Yet every measurement tightens the mystery. Supernova surveys, galaxy maps, and even gravitational waves all point to the same unsettling truth. Dark energy is real, it's dominant, and it's rewriting the destiny of everything. The universe isn't just drifting apart, it's being pushed, and whatever's doing the pushing remains one of science's greatest enigmas, a reminder that the cosmos still holds cards it hasn't shown us. So when you look up at the night sky, remember, those stars aren't just distant, they're fleeing, and the farther they get, the faster they'll go, a silent testament to the invisible hand shaping the fate of all things. Some planets don't orbit stars at all. They drift through the galaxy's dark voids like cosmic nomads, untethered from any solar system. These rogue planets, flung from their birthplaces by gravitational chaos or born alone in interstellar nurseries, might outnumber stars in the Milky Way by as much as 20 to 1. Picture Earth ripped from the sun's warmth, cast into the frozen depths of space, and you've got the basic idea, except these worlds are far stranger than simple frozen wastelands. How does a planet get exiled? Young solar systems are violent places, with gravitational tug-of-wars between massive planets often kicking smaller siblings into the abyss. A close encounter with a gas giant or a passing star can send a planet spiraling away, its orbit stretched until it breaks free entirely. Some might even form directly from collapsing gas clouds, never knowing the warmth of a star's light. The result is a population of invisible drifters, too faint to spot unless they pass directly in front of distant stars or reveal themselves through the faint heat of their lingering formation energy. But here's the twist: these frozen outcasts could be hiding life. Without a sun, you'd think their surfaces would be barren, but deep beneath ice sheets, tidal forces or radioactive decay might maintain vast subsurface oceans. Take Jupiter's moon Europa, a world heated by gravitational squeezing as it orbits its giant planet. A rogue planet with a similar underground sea, kept liquid by internal heat or insulating ice layers, could harbor microbial extremophiles or even more complex organisms. Some models suggest geothermal vents, like those on Earth's ocean floors, might persist for billions of years, serving as oases in the eternal dark. The possibilities get wilder. Rogue planets with thick hydrogen atmospheres could trap enough heat to create surface temperatures above freezing, defying expectations. Others might host floating microbial life in high-altitude atmospheric layers, surviving on chemical energy rather than sunlight. And if two rogue planets collided, the energy released could temporarily melt their surfaces, creating fleeting pools where life might spark before freezing solid again. Astronomers are just beginning to hunt these ghosts. Projects like the Nancy Grace Roman Space Telescope aim to detect them through microlensing, watching for the way their gravity bends light from background stars. Each discovery peels back another layer of the mystery, challenging our assumptions about where life can thrive. So while these worlds float unseen in the darkness, they remind us that the universe doesn't play by Earth's rules. Life might not need a sun, a solar system, or even a surface, just a pocket of liquid and time. The galaxy could be teeming with such hidden refugees, carrying their secrets through the void. Deep in the cosmos, there's a structure so vast it defies our understanding of how the universe should be organized. The Hercules Corona Borealis Great Wall, a sprawling chain of galaxies stretching an astonishing 1.4 billion light-years from end to end. To put that in perspective, if you could travel at the speed of light, it would take you 1,500 times longer to cross this wall than it has taken humanity to evolve from our earliest ancestors. This isn't just a cluster of galaxies, it's a cosmic continent, a filament of superclusters bound together by gravity's invisible threads, and its existence might rewrite the rules we thought governed the universe. What makes this wall so puzzling? According to the cosmological principle, a cornerstone of modern astronomy, the universe should look roughly the same no matter where you observe it from. On large enough scales, matter should be evenly distributed like foam in a well-stirred latte. But the Hercules Corona Borealis Great Wall throws that assumption into question. It's not just big, it's too big, far larger than theoretical models predict should be possible. If the universe were truly uniform, colossal structures like this simply shouldn't exist. Here's how astronomers stumbled upon it. By mapping gamma-ray bursts, the violent, high-energy explosions marking the deaths of massive stars. These bursts act like cosmic breadcrumbs, tracing the locations of galaxies too distant and dim to see directly. When researchers plotted thousands of them, they noticed an eerie pattern, a dense concentration of bursts in one region of the sky, revealing an immense galactic wall hiding in plain sight. The sheer scale of it suggests that, on some level, the universe might be more lumpy and less uniform than we ever imagined. But not everyone's convinced this wall is a true structure. Some scientists argue it could be a trick of perspective, an illusion created by multiple galaxy clusters lining up along our line of sight. Others propose that dark matter, the invisible scaffolding of the cosmos, might have funneled galaxies into these vast web-like formations over billions of years. If true, it wouldn't violate the cosmological principle so much as stretch its limits, showing that even in an evenly distributed universe, gravity's tug can sculpt staggering irregularities. The debate matters because it cuts to the heart of how we understand the universe's origins. If structures this colossal are real, they might hint at exotic physics, primordial forces, or fluctuations from the Big Bang that imprinted these gargantuan blueprints on the cosmos. Imagine throwing a handful of confetti into the air, only to watch it arrange itself into a perfect spiral. That's how unexpected this wall seems. For now, the Hercules Corona Borealis Great Wall remains one of the universe's most tantalizing mysteries, a shadowy leviathan lurking at the edge of our maps. Whether it's a flaw in our theories or a sign of deeper, undiscovered laws, it reminds us that the cosmos always has another surprise up its sleeve, and the more we explore, the stranger it gets. The moon isn't as silent as it looks beneath its dusty surface. The ground shakes with moonquakes, tremors that can last up to 10 times longer than earthquakes. These aren't just rare shivers, some of them register as high as 5.5 on the Richter scale, strong enough to rattle equipment and send loose regolith sliding in slow-motion avalanches. But unlike Earth's quakes, which come from shifting tectonic plates, lunar tremors have far stranger origins. Most moonquakes happen deep underground, triggered by tidal forces as Earth's gravity stretches and squeezes the moon like a rubber ball. Just as our oceans rise and fall with the tides, the moon's rocky body flexes, creating cracks and stresses that release energy in sudden jolts. Others come from meteor impacts. Even small space rocks hitting the surface can send vibrations rippling through the brittle lunar crust for hours, bouncing around like echoes in a cavern. The most puzzling ones, though, are the shallow moonquakes, originating just a few miles below the surface with no clear cause. Some scientists suspect these might be linked to cliffs created as the moon's shrinking crust buckles, a reminder that even dead worlds can still shift and settle. This isn't just a lunar curiosity, it's a serious challenge for future moon bases. On Earth, engineers design buildings to withstand quakes that last seconds. On the moon, structures would need to endure vibrations that linger for half an hour or more, like a tuning fork humming endlessly in a vacuum. A habitat shaking non-stop for that long could fatigue materials, crack airtight seals, or destabilize solar arrays. NASA Artemis missions are already studying these tremors, mapping the moon's seismic hotspots to avoid placing critical infrastructure on shaky ground. Here's the kicker: some researchers think moonquakes could actually be useful. The way seismic waves travel through the moon's interior reveals secrets about its structure, like a sonogram of its core. Future colonists might even harness the vibrations to generate energy, turning a geological hazard into a resource. But one thing's certain: anyone living on the moon will need to get used to the ground moving beneath their feet in ways Earth never prepared them for. The moon isn't just a static rock in the sky. It's alive with hidden tremors, whispering the story of a world still shaped by forces both ancient and unseen. Space isn't the silent void we imagine. It's alive with vibrations, a symphony of plasma waves and electromagnetic whispers just waiting to be heard. While sound as we know it can't travel through the vacuum, the cosmos hums with energy that NASA has learned to translate into eerie, haunting sounds for human ears. These aren't just random noises, they're the voices of planets, stars, and magnetic fields, converted from data into something we can finally experience. Take Saturn, for example. When the Cassini spacecraft dove through the gap between the planet and its rings, its instruments detected plasma waves rippling through the charged particles there. Scientists scaled these vibrations down to frequencies our ears can detect, and the result was a ghostly chorus, crackling, hissing, and wailing like a storm of cosmic static. Or listen to Jupiter, where Juno recorded the interactions between its magnetic field and the solar wind, producing a series of eerie clicks and whistles that sound straight out of a sci-fi soundtrack. But how does this work? Space is filled with ionized gas called plasma, and when charged particles move, they create electromagnetic oscillations, a kind of invisible music. These waves can't travel as pressure waves like sound on Earth, but they can be measured as fluctuations in electric and magnetic fields. By shifting these frequencies into our audible range, NASA lets us hear phenomena that would otherwise slip past our senses. Some of these space sounds are downright unsettling. The black hole at the center of the Perseus galaxy cluster, for instance, sends out pressure waves that ripple through the surrounding hot gas. In 2022, astronomers took those waves, originally 57 octaves below middle C, and boosted them by quadrillions of times to create a chilling, discordant drone. It's the deepest note ever detected, resonating for billions of years, now compressed into something we can actually perceive. Then there's Earth's own magnetic shield, which belts out a protective tune as it deflects solar winds. Converted into sound, these interactions resemble an otherworldly choir, modulating in pitch as solar activity ebbs and flows. Even the Voyager probes, now drifting in interstellar space, have picked up the faint hiss of plasma, the signature of the sparse gas between stars, vibrating with the echoes of ancient supernova. What makes this more than just a curiosity is how it reshapes our connection to the cosmos. For centuries, we've explored space with our eyes, telescopes capturing light, cameras snapping images. But now we're learning to listen, uncovering layers of the universe that were always there, just beyond our perception. These sounds aren't merely translations, they're reminders that the universe communicates in ways we're only beginning to understand. So the next time you gaze at the stars, remember, they're not just shining, they're singing. Every 11 years, like clockwork, the sun performs a cosmic magic trick. Its magnetic poles flip. North becomes south, south becomes north, in a celestial switcheroo that sends ripple effects throughout the solar system. This isn't some abstract celestial quirk. It's a fundamental part of the solar cycle, a rhythm as reliable as the seasons, but with far more dramatic consequences. The sun's magnetic field is generated by the churning of plasma deep inside it, a process called the solar dynamo. Over time, the magnetic field grows increasingly tangled, like a rubber band twisted too tightly, until it finally snaps and realigns. When the flip happens, it's not instantaneous. The transition can take months, with magnetic chaos reigning as the sun's poles wobble, weaken, and eventually reverse. During this period, sunspots and solar flares become more frequent, turning our star into a tempest of unpredictable activity. One of the most visible effects of this reversal is the surge in space weather. Coronal mass ejections, massive bursts of solar wind and magnetic fields, can bombard Earth, creating dazzling auroras that dance far beyond their usual polar stages. These geomagnetic storms paint the sky in surreal greens and purples, visible as far south as the tropics under the right conditions. But there's a flip side to this beauty. That same solar fury can fry satellite electronics, disrupt GPS signals, and even knock out power grids on Earth. In 1989, a solar storm plunged Quebec into a 9-hour blackout, leaving millions without electricity. Just a taste of what an extreme event could do today in our hyper-connected world. The upcoming flip, expected within the next year or two, could bring some of the most intense auroras in decades, especially as the sun approaches solar maximum, the peak of its 11-year cycle. But it's not just about pretty lights. Scientists are watching closely because these magnetic upheavals act like a stress test for Earth's defenses. Our planet's magnetic field shields us from the worst of the sun's outbursts, but during a reversal, cracks in that armor can appear, letting more solar radiation slip through. Satellites in high orbits are particularly vulnerable. Without the protection of Earth's atmosphere, they're sitting ducks for charged particles that can short-circuit delicate circuitry. Even astronauts on the International Space Station might need to take shelter in more heavily shielded areas during severe solar storms. Some researchers worry that a worst-case scenario, a so-called Carrington-level event like the solar superstorm of 1859, could cripple global communications for weeks or longer. Yet this magnetic dance isn't just a hazard, it's a chance to learn. Each flip gives scientists fresh clues about the sun's inner workings, helping refine models to predict space weather more accurately. Missions like NASA's Parker Solar Probe are diving closer to the sun than ever before, gathering data that could one day give us advance warning of dangerous eruptions. So while the sun's poles prepare to trade places, remember, this isn't just a distant astronomical event. It's a reminder of how deeply we're tied to our star's whims and how much we still have to learn about the forces that shape our place in space. The flip might be routine for the sun, but for us, it's a front-row seat to one of the solar system's most spectacular shows. Mars isn't just home to the tallest volcano in the solar system, it's the site of a geological behemoth so colossal, it makes Earth's greatest mountains look like molehills. Olympus Mons doesn't merely dwarf Mount Everest, it laps it 3 times over, standing a staggering 16 miles high. That's so tall, if you stood at its base, the summit would vanish beyond the curve of the planet itself. But what's truly mind-bending isn't just its height, it's the sheer scale. This volcano sprawls across an area the size of Arizona, with slopes so gradual you wouldn't even feel the incline if you hiked them. The secret to Olympus Mons' monstrous size lies in Mars' low gravity, just 38% of Earth's. On our planet, massive volcanoes like Hawaii's Mauna Loa eventually collapse under their own weight, cracking and sliding in a process called gravitational spreading. But on Mars, weaker gravity lets lava pile higher and wider without crumbling, like building a sandcastle with fluffier sand. And without tectonic plates shifting beneath it, Olympus Mons had the luxury of sitting over the same magma hotspot for billions of years, growing layer by layer into the solar system's most imposing landmark. Here's what makes it even wilder. Olympus Mons isn't just big, it's old. While Earth's volcanoes sputter to life and die in millions of years, this Martian giant had perhaps 3 billion years of uninterrupted eruptions. Picture a fire hose of lava turned on and left running for longer than complex life has existed on Earth. The result, a mountain so vast its caldera, the bowl-shaped depression at its summit, could swallow entire cities with cliffs taller than the Grand Canyon encircling it. But don't pack your climbing gear just yet. Mars' thin atmosphere means no oxygen at the summit, and temperatures hover around -70 degrees Fahrenheit even on a good day. The real challenge, the mountain slopes are littered with house-sized boulders and dust drifts deep enough to swallow a rover whole. Olympus Mons isn't just a record breaker, it's a time capsule. Its ancient lava flows preserve snapshots of Mars' volcanic heyday, when the planet crackled with geothermal energy and rivers of molten rock carved the landscape. Today, it stands silent, a monument to a time when Mars was as geologically alive as Earth, and a reminder that even in the cosmos, size isn't about strength. Sometimes it's about patience. Mercury, the planet closest to the Sun, is a world of extreme surface temperatures can soar to 800 degrees Fahrenheit, hot enough to melt lead. Yet hidden in the perpetual darkness of its polar craters, shielded from the scorching sunlight, lies something astonishing: vast deposits of water ice. This discovery shattered our assumptions about the solar system's most torched planet, proving that even in the most unforgiving environments, the universe hides its secrets in plain sight. These icy reservoirs exist because Mercury's rotation is tilted just right, or rather, hardly tilted at all. Its axis is almost perfectly vertical, meaning some craters near the poles never see sunlight. Their floors plunge into eternal shadows, creating natural freezers where temperatures can plummet to -300 degrees Fahrenheit. Over billions of years, comets and asteroids delivering water to Mercury's surface left behind ice that never had a chance to vaporize, locked away in these frozen vaults. The first hints came in the 1990s when Earth-based radar telescopes detected unusually bright reflections from Mercury's poles, signatures eerily similar to ice. But it wasn't until NASA's Messenger mission in 2012 that scientists got definitive proof. The spacecraft mapped these shadowy regions, confirming not just water ice but also organic compounds, the building blocks of life trapped alongside it. Some deposits are up to 65 feet thick, enough to bury a 6-story building. Here's what makes Mercury's ice even more bizarre. Some of it is coated in a mysterious dark material, likely carbon-rich organics or complex hydrocarbons. This layer acts like cosmic sunscreen, protecting the ice beneath from the faint heat of distant stars and the solar wind. It's a preservation technique the universe invented long before we ever dreamed of refrigeration, a natural deep freeze with its own insulation. This discovery forces us to rethink not just Mercury but the entire inner solar system. If a planet this close to the Sun can harbor ice, where else might it be hiding? The Moon has similar shadowed craters at its poles, and even Venus, though its surface is hellishly hot, might have traces of ancient ice lingering in its atmosphere. Mercury's ice also raises tantalizing questions about how water, a prerequisite for life as we know it, is distributed across the cosmos. Could these frozen caches have been delivered to Earth in its infancy, kickstarting our own oceans? For future explorers, these ice deposits could be game-changing. Water isn't just for drinking, it can be split into hydrogen and oxygen for rocket fuel or breathable air, making Mercury a potential pit stop for deeper solar system missions. Imagine a lunar-style base nestled in one of these craters where astronauts could mine ice under the dim glow of starlight, shielded from the blistering heat just a few miles away. Mercury's ice is a paradox wrapped in a riddle. A planet where metals pool in molten lakes on the surface also guards frozen water in its darkest corners. It's a reminder that the universe never follows the rules we set for it, and that sometimes the last place you'd think to look is exactly where the answers are waiting. Venus doesn't just move to the beat of its own drum, it rewrote the rhythm of time itself. On this smoldering world, a single day, the time it takes to complete one full rotation, lasts 243 Earth days. That's longer than its entire year, which zips by in just 225 Earth days. Wrap your head around that. If you lived on Venus, you'd celebrate your birthday before you could even finish a single sunrise to sunrise cycle. You'd literally age faster in Venusian years than in Venusian days. This bizarre time warp happens because Venus spins agonizingly slowly and backward. While most planets rotate counterclockwise like Earth, Venus flips the script with its retrograde rotation, turning clockwise at a glacial pace. Picture a clock running in reverse, its hands crawling so lazily that the sun appears to rise in the west and set in the east, taking months to cross the sky. A Venusian sunrise isn't just a daily event, it's a seasonal spectacle. The real kicker, Venus' thick, toxic atmosphere spins 60 times faster than the planet itself. Hurricane-force winds whip clouds around the globe every 4 Earth days, creating a permanent superstorm that drags the upper atmosphere along like a runaway carousel. This disconnect between surface and sky means that while the ground below barely moves, the sky above races by in a blur of sulfuric acid and crushing pressure. Scientists still debate how Venus became such a cosmic oddball. The leading theory, a cataclysmic collision billions of years ago, perhaps with a protoplanet the size of Mars, knocked Venus sideways and reversed its spin. Others argue gravitational tugs from the Sun and other planets, combined with tidal forces from its thick atmosphere, could have slowed and flipped it over eons. Either way, the result is a world where time itself feels broken. Living on Venus would warp your sense of reality. Imagine a work week lasting decades, or seasons changing faster than the hour hand on a clock. A child born at dawn might see their first sunset as a retiree, and with surface temperatures hot enough to melt lead and pressures like being half a mile underwater, your lifespan would be measured in sunrises, not years. Yet Venus' backward clock isn't just a curiosity, it's a cautionary tale. Unlike Earth, Venus has no magnetic field to shield it from solar winds, leaving it vulnerable to radiation and atmospheric erosion. Its sluggish rotation might even be linked to its runaway greenhouse effect, a warning of how delicate planetary balances can spiral into extremes. So while we marvel at its topsy-turvy timeline, Venus reminds us, in the cosmos, the way a planet moves can shape whether it thrives or becomes a cautionary wasteland. What if everything you see, touch, and experience, every star, planet, and galaxy, is nothing more than an elaborate illusion? Some of the brightest minds in physics are seriously considering this possibility, known as the holographic principle. The idea suggests our three-dimensional reality might actually be encoded on a distant two-dimensional surface, like a cosmic projection, a universe-sized version of the holograms on your credit card. This mind-bending concept didn't spring from science fiction. It emerged from one of the most perplexing puzzles in physics: what happens to information that falls into a black hole? According to quantum mechanics, information can never truly be destroyed, but black holes, with their voracious appetites, seem to violate this rule by swallowing particles and the data they carry without a trace. In the 1990s, physicist Leonard Susskind and others proposed a radical solution. Maybe the information isn't lost, it's just smeared across the black hole's event horizon, the boundary where gravity becomes too strong for even light to escape. Like an artist painting a scene on a flat canvas, the black hole could encode everything that falls into it onto its two-dimensional surface. The implications of this idea stretch far beyond black holes. If a black hole's interior can be described entirely by information on its outer shell, could the same be true for the entire universe? Some versions of string theory suggest our three-dimensional cosmos might be a projection from a two-dimensional boundary at the edge of space-time, a place where all the information about reality is stored like pixels on a screen. In this view, the world we perceive is akin to a movie being played back in 3 dimensions, while the real data exists elsewhere, written in a language of quantum bits we can't yet decipher. Here's where it gets even stranger. The holographic principle could explain why our universe seems to have an upper limit on how much information any region of space can contain. Just as your computer screen can't display infinite detail, space itself might have a maximum resolution set by Planck-scale pixels far smaller than atoms. This could unite two conflicting pillars of physics, quantum mechanics and general relativity, by showing how gravity emerges from quantum information dancing on the edges of reality. Evidence for this wild idea is still speculative, but tantalizing clues exist. Certain calculations in quantum gravity produce identical results whether performed in 3 dimensions or their 2-dimensional equivalents, hinting at a deep connection. Even the cosmic microwave background, the afterglow of the Big Bang, has been scrutinized for patterns that might reveal an underlying pixelated structure. If the holographic principle holds true, it would mean your morning coffee, the smartphone in your hand, even the thoughts in your brain are all part of an immense cosmic code, a shadow play cast by interactions on a distant, flat frontier. Reality, as we know it, would be the most convincing illusion of all. Every atom in your body, the calcium in your bones, the iron in your blood, even the gold in your jewelry, was forged in the heart of a dying star billions of years ago. That oxygen you're breathing right now, it was violently blasted into space by a supernova explosion before the Earth even existed. The carbon that forms the backbone of your DNA. It was crafted in the searing furnace of a red giant star, then scattered across the cosmos to eventually become part of you. We don't just observe the universe, we carry its most dramatic history inside us. Think about the last time you held a newborn baby. That child's tiny fingers contain stardust older than our solar system, remnants of stellar explosions so powerful, they briefly outshone entire galaxies. The gold in your wedding ring was likely born when 2 neutron stars collided in a cataclysm so energetic it warped space-time itself. Even something as simple as the salt on your dinner table contains sodium atoms that have been traveling through the galaxy since before the moon formed. This isn't poetic exaggeration, it's hard astrophysics. In the beginning, the universe contained only hydrogen and helium. The heavier elements, the stuff of planets and people, could only be created under the extreme conditions found in stars. Smaller stars like our Sun gently shed their outer layers, sprinkling space with elements like carbon and nitrogen. But the truly spectacular forging happens when massive stars die in supernova, their final moments so intensely hot and pressurized that they create elements like iron, gold, and uranium in a single brilliant flash. Even more exotic elements might form when ultra-dense neutron stars collide, spraying precious metals across interstellar space like cosmic glitter. The profound implication. Your very existence is the universe becoming conscious of itself. Those ancient stars had to die and explode so that one day, billions of years later, their material could coalesce into a planet where life could emerge. The same calcium that once helped a star burn now lets your muscles move. The same iron that glowed in a supernova's heart now carries oxygen through your veins. You're not just made of stardust, you're the universe's way of remembering its own dramatic past. When you look up at the night sky, you're not just seeing distant points of light, you're gazing at your extended family. Every twinkling star is a potential cousin, another link in the chain that led to your existence. The next time you feel small or insignificant, remember, you're the universe experiencing itself, crafted from the ashes of cosmic giants, walking proof that stardust can wonder about its own origins. Our connection to the cosmos isn't just spiritual, it's written in every cell, every breath, every heartbeat. We aren't in the universe, we are the universe contemplating its own grandeur. We've journeyed through a universe that defies imagination, where black holes slow time to a crawl, diamonds the size of planets drift through the void, and the night sky is a time machine showing us echoes of the ancient past. But perhaps the most humbling revelation is this: everything we think we know might just be a cosmic illusion. The holographic principle whispers that our 3D reality could be nothing more than a shadow play, pixels on a distant 2D surface we'll never see. And dark matter, that invisible puppeteer shaping galaxies without ever showing its face, it's still out there, taunting us with its secrets. These aren't just facts, they're invitations. Every mystery we've uncovered is a door waiting to be kicked open, a puzzle begging to be solved. Maybe you're the one who'll finally crack dark matter's code or spot the glitch in the universe's hologram. The cosmos doesn't give up its secrets easily, but that's what makes the hunt so thrilling. So stay curious. The universe has spent billions of years setting up these riddles. It's our turn to chase the answers. Hit subscribe to join us as we keep unraveling the cosmos, one mind-bending revelation at a time. And drop your favorite fact in the comments. Was it the diamond planet, the sideways raining glass, or something even weirder? The universe is stranger than fiction, and the next chapter is yours to write. Keep looking up. The greatest discoveries are still out there, hiding in the dark.